mass at Georgia Tech. So to introduce the lab, the purpose is to learn about the motion of objects dropped from rest. And to do this, an experiment is run by dropping a paper ball from rest. Then the results of that motion are compared to two different computational models, one that only considers gravity and one that considers both gravity and drag. So some important background information. A formula that is needed to know is the formula for gravitational force. It says that gravitational force equals negative mg times j hat. Lowercase g is 9.8 newtons per kilogram, which is Earth's gravitational force. Lowercase m is mass, and j hat is the direction 0, 1, 0. Since the ball's position isn't moving in the x or z direction, the only value that's not 0 is in the y direction. Another important formula is the formula for drag. The force of drag equals negative b v squared times v hat. B is the proportionality constant, v is the object's speed, and v hat is the velocity direction. The magnitude of the gravitational force is greater than the magnitude of the drag force. Therefore, the net force acting on the object is pointing downwards, meaning that when the object is dropped from rest, it falls to the ground. This is a screenshot from my tracker information. As you can see, as I drop the ball, the position versus time graph is shown on the right. This is my code that I edited to use for the computational model that only considers gravity. I weighed the paper ball and inserted that for the mass. I used the tracker information to define the initial position vector. Since the ball is starting at rest, the initial velocity vector is 0. The gravity on Earth is 9.8. The j hat, as discussed before, is 0, 1, 0. And because this model is not considering drag, I set the b equal to 0. I used the timestamp recorded in tracker to set my time loop. Then I used the formula for gravitational force found in the slide before to set the variable w equal to gravitational force. And because only gravity is being considered for this model, F net equals w. Then I used the velocity update formula, which says that v final equals v initial plus F net divided by mass times delta t, to update the velocity, and the position update formula, which says the final position equals the initial position plus the average velocity times delta t. This is the resulting graph from that model. Then I used the GlowScript model including drag. Only a few things were changed. I changed b, which I set equal to 0.0248. This b was calculated by running the code until the final data point from the observed experiment is reached. Then I had to change my formula for the net force. W stays the same, but I had to find an equation for the drag force. I used the drag force formula from the background information to set the variable Fd. Then I added that to W in the Fnet equation to find the Fnet equals the gravity force and the drag force combined. This is a graph comparison of all three: the observed data, the computational data that only computes gravity, and the computational data that includes gravity and drag. As you can see, the observed data in dark blue is closest to the computational model that includes both gravity and drag. This means that it's likely that gravity and drag were acting on the paper ball when it was dropped, not just gravity. There are many possible sources of error in this experiment. There could have been calculation errors because room for human error is always present. I could have easily made a miscalculation or coding error that changed the results of my experiment. Additionally, outside forces could have caused a source of error. Because the video is filmed in the real world, numerous outside forces such as wind or naturally occurring forces could have affected the path the paper ball took. Now, the discussion questions. What if and what does it mean? When looking at the velocity versus time graph of the motion, we can see that when only gravity is computed, terminal velocity is not reached, but when gravity and drag are computed, terminal velocity is reached. Additionally, the paper ball being thrown backwards would not change the terminal velocity. It would just cause the ball to reach that terminal velocity more quickly.